All right. Welcome to day 2 of midterm review. So today, we are going to pick up where we left off yesterday and do a bunch more examples of various topics and talk about, tips and tricks, ideas for solving them, and also just to review the kinds of things we've been doing. So let's get started. So the first problem I think we are going to pull from, again, back close to the beginning of the summer. And this was from when we were just discussing how to do proofs. So the idea here is, basically, I want to talk a little bit about some more proof ideas. And in particular, there's one idea that I want to push, which is that, let's say you're looking at a problem, and it's not clear to you how you're going to solve it. So in this case, we've seen problems like this in the past. We've done square root of 2, we've done square root of 3. I think the practice midterm had cube root of 2 on it. But this is a slightly different situation because 6 is not a prime number. And in all of these proofs, we use some fact that if, p divides n squared, then p divides n. Or something like, if p divides ab, then p divides a or b. These kinds of things were sort of the kinds of things we were doing. Oh, maybe that should be bigger. When we were solving these problems. So now, it's not quite as clear if the same thing is going to work, because 6 is not a prime. But the idea that I want to emphasize with this example is that even if you don't know how a proof is going to go, it's a good idea to start going through it and see where you get hung up and see if you can fix these problems. Because I will acknowledge that writing proofs is hard, but I want to encourage you to think about it in terms of, if you take it one step at a time, then it may be that you can do each step, even if you did not think that you could do it from the start. Okay, so that's a lot of waffling, but let's prove this. So how did the proofs normally go? We proceed by contradiction. And again, in the spirit of giving tips, this is something that I've said many times, but let me say it again. Why are we going to do this by contradiction? It's because that gives us something extra to work with in this situation. Because writing root 6 equals a over b is something concrete to work with. So for example, in proofs where you're trying to show something is irrational, this is kind of a common theme. It is often easier to assume that it is rational and find a contradiction. So let's do that. So suppose root 6 is rational, and write root 6 equals a over b in lowest terms. Okay. And maybe also I want to treat this as an example of how to model a new proof off of proofs that you already know. So if you remember, how did we prove these cases? What we said was, let's square both sides to get rid of the square root, and then prove that a and b are both even or both divisible by 3. Something like this. So let's try and follow the same strategy and see if we get hung up. Then squaring both sides, 6 equals a squared over b squared. And rearranging a little bit more, 6b squared equals a squared. Now this is where we want to start talking about divisibility. And this is where we need to worry that 6 is not a prime, like we are used to. And so let's think about what kind of problems this causes. We want to say, or if we were following this proof exactly, we would say something like, since 6 divides a squared, we also have 6 divides a. And I don't think we've proven this because 6 is not a prime. But if we think carefully about this, it's not true only for primes. So that is one direction we could take, is prove this works for 6 also. So let me put this in brackets since this is not, we're not including this step yet. But another direction we could take is to go in a slightly different tack than going directly here and say that maybe we don't care that this number specifically is 6. Maybe we just want to say that this is even. So we can actually maybe follow even more directly, get the proof, and say, so 6 divides a squared, or let me write this down here. Another strategy is, since 6 divides a squared, we have 2 divides a squared, because 2 is a factor of 6. So 2 divides a. And now we're running with essentially the same argument we've used in the past. So just to say, both of these strategies will work. But I hope this is an example of how you might be working your way through a proof and come to a point where you don't exactly know what to do, but being able to generate new ideas based on what you've seen before, and then find a new direction. So I think this, we're going to ignore this one and carry on with this one. And now we can finish the proof in probably a similar way. So 2 divides a. Write a equals 2k for some k. Then returning to our equation here, we have 6b squared equals 4k squared. And now, if we divide both sides by 2, 3b squared equals 2k squared. And now we see that we need still a little bit of additional maneuvering, because we need to maybe, if we want to be very precise, include a slight extra step to conclude that 2 divides b squared rather than just something here. But we can do that because 2 is a prime. So 2 divides 3b squared, and 2 does not divide 3. So 2 divides b squared, so 2 divides b. And now we have gotten where we want to. So this is the usual contradiction that we get in these problems. We assume this fraction is in the lowest terms, and then we show that they both have a common factor. So contradiction.